Okay, now we just discussed this waving hands and stuff, and people came to the right conclusion. But let's draw it out on the board. Okay, when we use the generator, crank forward, crank backward, crank forward, crank backward, forward, backward. We were giving something very much like a square wave voltage. Okay, it wasn't exactly square, it wasn't exactly level up here and down here, but the principle is very much the same. Okay, then using a large capacitor with some resistance and so forth, we saw that the capacitor, wherever it is, and for reasons that are obvious from the solution of the equations and all the graphs that we looked at and everything else, if you really understand exponential functions and exponential approach to a limit, okay? There are capacitor voltage, let's use green, okay, blue. Okay, our capacitor voltage wants to approach this voltage. Now I've got it approaching too closely because I was talking and not thinking, but let's try again. Okay, now if this voltage continued without reversing, the capacitor would approach this limit as an exponential. So we continue along this curve, but you pull the rug out from under it, reverse the voltage. Well, now it's going to approach this voltage, okay? So now it comes down, same basic idea. It looks like it gets halfway up to this voltage in about this distance, okay? So kind of the half-life of this thing is about this far. So in about the same distance, it'll get twice as close to this one. Now, twice as close to this one, I think we've done this before. Twice as close to this would be down to about here. So you're going to have an exponential that kind of does this. And then it's, of course, approaching the limit down here, okay? And it continues approaching it until it gets here. And then you switch the voltage on it again. And then it goes up here. Same half-life, halfway would be about here. So it's probably going to go through this point, and it would approach, and then it comes back down here. Doesn't come back until you switch the voltage, though. So I went up to the half-life here, but I didn't go to here, and then it comes back down here, probably through about here, and so forth. Okay. Now, the point is that when this gets to a stable configuration, and I think we worked out the mathematics of this, when this thing gets to stable configuration, the capacitor voltage goes through zero after the source voltage goes through zero, okay? Because when the source voltage reverses, presumably it has a kind of instantaneous drop here, okay? It's not really what happens when you're cranking the thing, but that's what happens with a perfect square wave, if anybody ever gets one, okay? That perfect square wave is kind of an ideal, doesn't. Yeah, you never really can generate a perfect square wave, but you can reverse voltage in nanoseconds, okay? So it's essentially a square wave, and yeah, differences become not important. So anyhow, okay, so the source voltage is zero here, and here, and here, and here, right? Capacitor voltage zero. Well, that doesn't occur until here or here, and I haven't drawn this particularly well, but okay, capacitor voltage is zero here and here and here, at least course, it'll be more consistent, but you get the idea. Okay, so capacitor voltage is out of phase with the source voltage. Okay. Capacitor voltage lags the source voltage. Now, if you have a sine wave, so if your source voltage is doing this, you could kind of analyze this bit by bit. You could approximate this source voltage by, let's say your source voltage is this from here to here, then it's this from here to here, then it's this, and then it's maybe this and this. So your capacitor voltage would start out chasing this voltage, so it exponentially approach this voltage, but then it would exponentially approach this voltage and then exponentially approach this and so forth, okay? Now, again, when this voltage goes through zero, your capacitor voltage is going to be behind your source voltage. Also, it's going to be less than your source voltage. So if you start out here, your capacitor voltage is going to do something like this. Oh, went down too far. Be good if I can make myself think what we're doing there. Okay. There's a phase lag, and the voltage is different. Okay. Well, in a sense, then this capacitor circuit kind of has a resistance because voltage isn't as great as the source voltage, okay? And it has a phase lag, okay? So again, after a transition phase where it takes this thing time to smooth out, okay? Transition, the capacitor voltage becomes like a sine wave with less amplitude. In a phase lag. Okay. So again, here's your source. Here's your capacitor. And here's voltage. And here's time. Okay, it's implicit. Doesn't hurt to label it. Very good idea. Okay. So that the capacitor, and there's a resistance, so there's like an RC circuit, okay? But the capacitor acts like there's a resistance due just to the capacitor. Okay, the capacitor suppresses slow oscillations. okay? Fast oscillations, okay? If the oscillation's fast, it doesn't have time to build up any voltage, okay? If this is a very short time frame, then the half-life might be way out here, and it only gets up to here, and then it gets down to here, and okay? So fast oscillations are suppressed. Okay, well, then you have this thing called reactance. Okay, reactance is kind of like resistance, but it involves a phase leg and leads you to Phasor diagrams, which are really neat. Now I want exposure to that, okay? So we're going to do a little bit more. Now, we're not going to do the complete derivation, which requires pretty much the techniques of a differential equations course. This is only half the class. It's had a differential equations course, and since it's beyond the scope of this first semester university physics course, we're not going to actually do it. If everybody had the differential equations, I'd probably write it out. It's a little more complex than the equations we looked at in lab last week. Okay, so let's develop this a little bit. Okay, we need to talk about this conceptually because we're not going to do all the mathematics of it. But you're going to get the picture. Okay, so I kind of misspoke. I said because there's a resistor and stuff like that. There's a resistor in this thing. Okay, but you have the capacitor and you have a resistor. Okay. The resistor might just be in the wires and have very low resistance. Okay. Now, if you have just a resistor in a circuit, the current through the circuit will exactly follow the voltage. There'll be no phase lag. Okay. And of course, the voltage across the resistor is just the current times the resistance, right? Okay. And the voltage across the resistor is always just the voltage of the source, okay? Or really, you want to kind of focus on the current. So we're going to do that, but okay. So you've got this resistance that doesn't lag, the current through the resistor doesn't lag the voltage, okay? But the current through the capacitor does lag the source voltage. Well, you put that together, and we've got to go a little further before we can really talk about that. Okay, well, the other thing though is an inductor. So you got this coil. And now you've got a source voltage that's driving a current, right? Okay, so what happens if you just have the source voltage on the inductor? Okay, how does the voltage through the inductor compare to the voltage of the source? And it turns out, and let's not get into the details of it right now, but it turns out that the voltage through the inductor precedes the voltage of the source. Okay, so now you could have a circuit where you have a capacitor tends to delay, but an inductor that tends to precede the voltage of the source. Okay, that's not hard to understand. I don't want to draw it out right now, though. And if you balance the effect of the capacitor and the effect of the inductor, you get what's called resonance. Okay, where the circuit theoretically builds voltage without limit and blows up. Okay. Now there are limits, you know, you got thermodynamic limits and all kinds of stuff that cause that not to really happen. That's totally analogous to the effect of a spring. Okay. If you push the spring at the right frequency, theoretically, it'll just keep increasing in amplitude, like a kid on a swing. Okay. If I push at just the right time, just a little tiny push, I can build up a lot of amplitude in that swing. Now, the chain of that swing is flexing and there's wind resistance and stuff. So there's a limit, and we never do kill the kid, which is not our goal. Okay. Our goal is not to kill the kid. So we're not going to we're not going to endanger the kid by pushing the swing because of dissipation of energy, okay? But at first, just a little tiny push, little tiny push, little tiny push, and get that kid swinging pretty good, okay? Totally analogous to matching the frequency of my push with the natural frequency of the swing. Now, an RC circuit or an RL circuit, an LC circuit, I'll get it right yet. An LC circuit has a natural frequency. You can solve the differential equation, which is the same as the differential equation you solve for a swing or a spring, okay? And we are going to look at that. So by matching the inductance to L, right, with the capacitance C, we can achieve any natural frequency we want. Okay, we will look at the mathematics of that. But what we really want to look at is reactance because we've kind of done the mathematics of that. So I'm going to do that kind of quickly. Okay, well, let's go ahead and do that mathematics just to make sure we have the idea of resonance. Okay, just quick review, I wrote this down. Okay, it's just your Newton's second law for a spring or a pendulum. For an ideal spring or an ideal pendulum, where there's no dissipation of energy. Okay, you get this equation, which translates to this, which gives you this, where omega is the square root of k over m. And that should be completely familiar to you. We've done that derivation a number of times, okay? And of course, you're doing differential equations, you're going to do a trial solution, x equals e to the RT, okay? And you're going to get r squared is going to equal negative k over m, so r is the square root of negative k over m, etc. Okay? So this is what we know, at least we need to know, now and forever, if you're going to be an engineer, okay? Until you find out that you're in a field of engineering where that's totally irrelevant, and that's kind of rare, okay? Okay. So Q double prime equals negative Q. This is the same equation this is. I'm just using L in 1 over C instead of M and K. The same reasons, and we talked about them, I think we talked about them last week. Omega is the square root of 1 over LC. Okay. I really need to understand that. Okay. If you drive this system at the same frequency as its natural frequency, so that's like you push a kid on the swing. Kid in the swing has a natural frequency till the amplitude gets big. Okay, you keep pushing at that natural frequency. So maybe you go up to the chain at the top of the swing, and you give it a little sine wave type thing like this. Okay, that's going to drive the system. Okay. And that's going to exert a force, actually a torque on the system. So it could be torque. It could be a torque of T. And you want to think about that. that's going to be, if your frequency matches the natural frequency of the swing, it's going to resonate, and you're going to get greater and greater oscillations. Okay. So let's say we got a, a frequency call this thing omega half. Then we get resonance. So your oscillation starts out low, gets higher, gets higher. Well, that's not my frequency. Within an envelope, two straight lines. Now, when I taught differential equation, we go through the details of this. I don't know if you've done the details of the approach to resonance, but it's worth looking at. Okay, so we're trying to understand. It involves some pretty heavy trigonometry, but it's good for your soul. Okay, there it is. And if you haven't taken differential equations yet and you don't do this, well, choices get made in the course and what to emphasize. Like you do a lot of Laplace transforms, you might not have time to do this. Okay, that's a typical choice. Or you do a lot of systems of equations, maybe you don't get to do this. It's too bad you don't get to do this. It's too bad you don't get to do everything, but you can't do everything. So a choice your instructor makes. Okay. Got to get a certain amount of stuff done, and there are all kinds of trade-offs. Then when I do this, I do less with Laplace transforms, or I expect more. I expect students to be able to do the integrations and develop the tables and stuff. Hope they will anyhow. Okay, so anyhow, so if you didn't do that, worth looking at. And if you take differential equations, as the rest of you will next year, kind of a capstone of systems of equations, not of higher order equations, second order equations. That's all you need. Okay, well, that aside, the mathematics is all mathematics that you should know if you had good trigonometry, good precalculus, whatever. And the same thing applies over here. So now, let me not use V for voltage and EMF. Symbol I should have been using. That's a bad looking E, it'll get better. Okay. EMF, right? Get this. And there's no end to it theoretically. But of course, there's energy involved, and energy is getting dissipated. So eventually it starts trailing off. Not before the feedback in that microphone makes everybody cringe. Okay, that's a resonance phenomenon. Okay. Okay, so we need to understand that the details of the mathematics are pretty hairy, okay, challenging even at the differential equations level. I'm not sure I understood it completely, assuming I do understand it completely, until I actually taught a differential equations course. Which I did in the first year of graduate school. But as an undergraduate, I knew it happened. I knew what mathematics was involved, but I couldn't reproduce it. until I actually had to. So, okay, well, there's that. So this happens if LC and omega have match. In other words, you can tune the circuit. Okay, and you have, you know, it used to be when capacitors were really capacitors. I mean, they are, but when they're, you know, like parallel plates, and you wanted to tune a television channel to resonate with the signal that was being broadcast through the air, you turn a little dial, which moves the capacitor plates a little further apart or a little closer together or something analogous to that. But change L, to change C, because it's much easier to change C than it is to change L. Now, actually, you can change L. You got an iron core in a loop, and you pull the iron core out a little bit, push it in a little bit. You could tune it that way, okay? And I'm not sure exactly how the old television sets were because they were really dangerous to get into because they were big capacitors and they could kill you. So we all knew not to mess with TV sets, okay? And the TV sets are big, I think they weigh hundreds of pounds, okay? Because all the electronics was, you know, vacuum tubes and electrolytic capacitors and stuff. And it was really, really, really hairy stuff. You had to make sure everything was discharged before you started touching things, okay? And people did get killed by the televisions. Everybody knew this, so nobody except really people with bad judgment got hurt. Because everybody was afraid of them, for good reason. Okay, well, that's history, okay? So that even kind of precedes the current events that we hear from across the hall in the 60s, okay? Because in the 60s, you started getting some integrated circuits and stuff like that. They got less dangerous. All right. In the 50s, we knew. And in the 60s, we kept those habits. Okay. Okay. You play around with the differential equations a little bit, and it really isn't that hard. If you've had a differential equations course, it's not hard to understand. You know, if you know the differential equations fairly well, where these expressions come from. But I'm just going to cut to the chase here. I had to look these up because I didn't have time to re-derive them, which I would normally do if we have time to do it. And I don't use them much. So I didn't think to look at them before class. But inductive reactance is omega times your inductance. Capacitive reactance is the reciprocal of omega times your capacitance. Omega is the frequency of your circuit. So the inductance changes if you change the frequency. Your reactance changes if you change the frequency, okay? And of course, your reactances change if you change the inductance or the capacitance. Depends on all three of these quantities, omega, L, and C. Now, the whole use of reactance, two things. One is that the voltage across your inductor is just your current multiplied by omega L. That comes out of the equations, okay? Just self-differential equations, and you call that then I times XL. So this comes out of the equations, and this leads to this definition of XL, which is the inductive reactance, okay? So this is inductive reactance capacitive reactance. But what's the voltage across your resistor? Well, it should be second nature to you now. If that's just current times the resistance, that's just Ohm's law. Most basic thing you know about circuitry, other than the whole conduction model. Okay, and how this comes out of the conduction model. Okay, so you got the voltage across the resistor is this. Well, these three things all have the same form. Okay, so now if we have a circuit consisting of an inductor and a capacitor and some kind of a voltage source, this is how we indicate periodic voltage source. And a resistor. We can now calculate, if we know the current, at any instant. If we know the current at any instant, we then know the voltage drop across the inductor, the voltage drop across the capacitor, and the voltage drop across the resistor. You know, I is just your I of t. It's dictated by whatever your source voltage function is, okay? So your source voltage would be like, I'll use the let's say E max cosine of omega t. This is going to give you a current I max, which is cosine of omega t plus phi. Okay. Now the phi is trick because voltage across the capacitor lags the driving voltage. Okay. So the current through the capacitor is going to tend to, well, going to depend on that lag. And the voltage through the inductor is going to be ahead of the driving voltage. So we got to work that out. And it turns out, well, let me tell you in a minute. Okay, I was about to draw you the picture of the Phasor diagram, but let's be clear on something. The question came up, was XL like the distance across or something like that? No, XL is omega L and XC is omega C. And XL acts like a resistance. If you got the current through your inductor, then you know the voltage across the inductor is current times XL. Just like the voltage across the resistor is current times R. Okay. Now the current's always the same. And current across the capacitor is the same as, you know, these three currents are all the same in this circuit, okay? So XL just acts like resistance, it suppresses voltage. XC acts like resistance, it suppresses voltage, okay? And resistance suppresses voltage. I say it suppresses voltage. It doesn't suppress voltage, it suppresses current, okay? The bigger XL is for given voltage, the smaller your current, right? Okay, so they act like resistances that suppress current for given voltage. But it's more complicated than that because these things are all out of phase. So I'm going to draw you a Phasor diagram. You've seen Star Trek, you know what phasors are. Well, that's not what phasors, that's not what their phasors are. First of all, standard circular model of a trigonometric function. Okay. Your driving voltage is omega t. Okay. So there's your driving voltage. And the radius of this circle is your maximum voltage. I'm not going to put that in because the diagram gets a little bit complicated. Okay. Now, the current through your resistor, looking for three colors here, current through your resistor maybe looks like this. Okay. Current through your capacitor lags the current through your resistor. So the current through your capacitor really bad. There's your current through capacitor. Yeah, okay. And it's not current, it's voltage. This is the resistance, not the capacitance. And then you have the voltage through your inductor, okay? Now, what's the net voltage? And also, being careless is out. This is your current, not your voltage. Okay, so this voltage through the inductor is 90 degrees out of phase with the current. And the voltage across the capacitor is 90 degrees out of phase with the current. So the current, you just imagine, current circular model of I max cosine omega t plus phi, okay? It's going to follow this circle. So, you're just going to go around here. Your current is going to be, if you're doing the cosine, is going to be this component of this vector. Okay. So current's going to be at maximum, then minimum, then maximum. That's going to give you your alternating current, and that should be a very familiar model since we used it many times during the course, starting with simple harmonic motion. Okay. During the 2 semesters. Okay. Well, there's your picture. Now, what's the result of those 3 vectors? Sketch me that picture and show me at that instant what the result of those 3 vectors would be. Okay, well, I say have these 3 vectors head to tail and see what you get. Now, the head to tail is much better than doing the components, but the components work. Now, what people wanted to do was say, okay, let's add the x components because you were talking about the cosine, right? Well, the x component of VR is like this. The x component of VC is like this. They're both positive. So if you add those x components, you get this plus this, which gets you out to about here. But then you got to subtract this. And this is a little bigger than this. So that brings you back to about here. So that would be the magnitude of your cosine. But that doesn't tell you much about phase relationships. If you add these vectors as vectors, just arrows head and tail, which is the way you add vectors, okay? Then you get this vector, and then we'll just add this one here, right? That gives you a vector from here to here. But now we've got to subtract this one. So this one acts opposite to this one. And there it is. Now that's our net force. And I'm looking for my orange chalk, but I'm not finding it. So I'll have to use yellow, which doesn't contrast as well, but it will be okay. Okay. Actually, well, I've got green up there. So right here, and that almost looks green. I really, oh, yeah, it's down there in the chalk. That's a bad place for it. Okay. Right there is the result of these three vectors and the tail. Okay. And this shows you this angle here which is phi, which I changed to theta naught for what seemed like a good reason, because I thought I was talking about this. I don't know. It's phi, just as I put it originally. Okay. That's your phase shift from your current. Now, a minute there, I thought I didn't have a good reason, but I'm not thinking about what I'm doing. Okay, I'm going to call that theta naught. So there's your I of t. Remember, I of t was this white vector here, right? And this voltage is out of phase by angle phi. Now, if you want the voltage to be in phase, you make VC and the VL equal and opposite. If VL is bigger than VC, then the phase of your net voltage, V of t, let's label that. Okay, here's your voltage V of t. It's out ahead of your current in this case. I had a sentence going there and I forgot the context of it, but what I'm saying now is if you want V of t to be in phase with your current, or if you want your current to be in phase with your voltage, whichever you wish, okay? Then your VL and your VC should be equal and opposite. So whatever your driving frequency omega is, you just match L, omega L with omega C, okay? You just manipulate your L and or your C to make these equal, and you're going to be in phase, okay? Well, there's a lot more to it, but that's the picture of a phasor. And it would be nice to be able to solve the equations and see where it comes from. It's a fairly short step, but it's gonna, it's just not something we can really do unless everybody just have differential equations, okay? If you've had differential equations, you ought to work it out. Typical second order equation. Now, the second order equation I mentioned, of course, I'm not going to ask you to do that here, just good for your understanding of differential equations. Your second order equation is this. It's a non-homogeneous equation that has sinusoidal solutions So you can do a trial solution and match everything up, okay? Undetermined coefficients, standard technique, the easier of the two techniques along with variation of parameters. If your E of t is not sinusoidal, then it's a little more complicated unless you want to use Laplace transforms. If you can Laplace transform this, it's easy to Laplace transform this equation, very easy. Gives you a simple algebraic equation, a quadratic equation, okay? Then you could solve it for a square wave or triangular wave or sawtooth. And, you know, some of the weird waveforms you can get maybe have to be approximated using Fourier series, and you haven't done that. So that gets a little bit beyond, that's more advanced course, okay? And if you're in a field of mathematics or of engineering where that becomes important, you'll have a more advanced course that teaches you to do that. Conceptually, Fourier series aren't particularly difficult. They're more difficult than Taylor series. Okay, anyhow, that's what you have. Now I should qualify that last comment. Conceptually, Fourier series aren't that much more, are conceptually on the same level as Taylor series, but Fourier analysis is way beyond. Okay. So, you know, Fourier analysis is just a huge area of applied mathematics. It goes into incredible depth. Okay, got to use all your linear algebra, all your calculus, and a whole lot of other stuff that you just have to develop. Okay, thinking about why an inductor has a voltage that is ahead of your current. Okay, it's basically because if you got a current flowing in your inductor doesn't want to let go of that current. Now, it doesn't have volition, okay, but it acts like it doesn't want to let go of the current. Why is that? Because if the current through a coil decreases, it's going to produce a voltage that prevents it from decreasing or that resists the decrease. Now it's going to decrease, but you know, the bigger the inductance, more reluctant it's going to be, or the more reluctant it's going to seem to release the current. Okay. So the current in the inductor drives a voltage, okay, it drives this current. So it's there before this current, okay? So it precedes the current, the phase precedes the current. Now we could analyze it and draw it. It's not as obvious as what it is for the capacitor, so I'm going to let you kind of think about that. Whether you totally understand it or not, you know, we're limited time. We've got like 90 minutes of class time left in the whole semester. So we need to move on to some review. But there you have the idea. Okay. Capacitor legs for the reasons we said, because when your current goes negative, your capacitor still got charge on it. Okay. The current doesn't go negative until your inductor stops pushing current, until the voltage of the inductor comes down to zero. Okay. So think about those things.